Hello students, I am going to start the new unit, strength of material. Strength of material. Actually, I am not able to. First of all, sorry for the late. I am not able to go on the Zoom or Skype because I thought that it is very time taking process and also very destructive process. It's temporary process, not a permanent option. So I thought to record my notes and just explain it. If you have got any problem, then kindly just poke me or reply me. Okay, so strength of material. Look at my handwriting is as you know, my handwriting is very bad, so kindly adjust it. So strength of material, why we are going to study so. Mm, it deals with highly required component functions which are used in electrical or mechanical. We are going to design which of any electrical mechanical structures or things which should not be break or bent or deform or any type of physical damage. That's why we are going to study so. We going to relate this subject from day to day life, like from small needle use to ship big submarines. It is easy to remember. It is very easy to remember it. It is very important in mechanicals or any designing purposes. This subject forms the basics of machine design and fluid mechanics, finite element analysis also. Here I have not written, I have just explained in the last class that what is rigid body and what is deformable body. First you have to understand between rigid body and deformable body. To rigid body means that suppose that what is rigid body. Look at I am going to just have it one body is there. If this two point I have located it, and if this two body if this two point are not changing distance, then it is called rigid body. When we apply any external force or any external momentum to this A and to this B, the body will not change its position, size or orientation, then it is called rigid body. And similarly it is opposite of what is deformable body. Deformable body is the distance between, suppose that this two point distance between A and B going to change when we are going to apply the external force applied, that is called deformable body. Sorry, it is A and B. So first you have to have very clear concept what is rigid body and what is deformable body. So rigid body is that bodies when we apply any external force or any external momentum to that AB, the distance between the two points does not changes, and simply it is opposite in deformable body. This is deformable body. When the distance between the point of AB changes when externally force is applied, that is called deformable body. In ideally no rigid body in the world. In ideally no rigid body is used in the world. Every body is deformable. So what is SOM? SOM deals with deformable body. You have studied also engineering mechanics. Engineering mechanics deals with rigid body. This is the main difference. In engineering mechanics, we have learned FBD, moment of inertia, and many important things like where the force is acting, how the free body is occurring. In whatever the case we have studied, that case is only studied in rigid body. But in SOM, strength of material, we are going to deal with the deformable body, like bending, twisting, etc. As a mining engineering student, you have to just have not got so much depth, because you have just a concept of stress or shear force bending moment I have also just given in the last unit when I am offline. And now we are going to know the stress. So we are going to start with the stress. Here in the stress it is written as it is the internal resistance to the external loading. Okay, it is the internal resistance to the external loading. It will be the internal property of the material, or stress is defined as the ratio of external load to the cross sectional area. So what do you mean by stress? Suppose that when externally load applied, suppose that one body is there. Wait a minute. One body is there. We are going to just have got tensile load. Just stretch it. It stops getting deformed. Ultimately, when we got applied load, this cross section area will become this cross section area, and this cross section become, suppose that it is A, it is B, it is now become B dash, it is now become A dash. So ultimate at a point when came, when A dash will the point one came when it is stopped being deformed after applying any external load. So whenever external load is applied, whenever external load is applied, whenever external load is applied, wait a minute, sorry, whenever external load is applied, some internal resistance develop. Whenever external load is applied, suppose that this is external load is applied, then one internal resistance is going to develop to bring back its original position, to bring back its original position. Okay, when here is external load is applied P, so for neutraling the P, for balancing the P, one internal resistance is applied. Okay, some applied, some internal resistance not applied, some external resistance developed to put the put the body back in its original position. So as we put the internal resistance, as the internal resistance is equal to the external load, then the deformation stops. Then the deformation stops. So internal resistance is directly proportional to deformation. Here the I have shown on body PPAB. Look at this body. One more example. Suppose that this is the body. Here the deflection is occurring del. Now this body is there. You see internal P, internal P, here A, here B, here C. Extension of the body has been deformed and it's in equilibrium. Body has been deformed and it's equilibrium. And just I will put the FPD of that body. This is that FPD of previously what I have done. Here is P is applied. We suppose that here P is applied and here A is. So internal cross-sectional area. At every point cross-sectional will be resist. At every point, this point, this point, this point, this point, at every point cross-sectional will resist or oppose, so distributed force will come into action. So at this point, every point, this will oppose that P, this will oppose the P, so distributed force will apply on the load. So net intensity F is equal to P. So here it is internal resistance. What is internal resistance? To external loading. When you applied internal resistance, when you applied the external load, the internal resistance is going to develop, that is going to call stress. One more difference is that what is P? P is equal to also F by A, and sigma, which is going to denote the stress, it is also be P by A or F by A. This is also load and this is also force. Here force is external and here P is internal resistance due to external load. So this is the difference. All the unit is also same, everything is same. So stress, it is the internal resistance to the external loading, or stress is defined as the ratio of external load to the cross-sectional area. Mathematically here we are going to write sigma is equal to P by A. P is what is external load. External A is equal to cross-sectional area. External load, load means Newton. Unit is Newton, cross-sectional area is mm square. What is the various unit of stresses? This is very important for numerical. 1 kilopascal. 1 kilopascal is equal to 10 to the power 3 Pascal. Pascal you have to write Newton per mm square, meter square. Newton for meter you have to change 10 to power 3 millimeter square. So therefore 1 kilopascal is equal to 10 to power 3 Newton by 10 to power 6 millimeter square. So 1 kilopascal is equal to 10 to power minus 3 Newton per millimeter square. This is very important. This is very important unit. You all have to remember for if you're going to solve the numerical. 1 kilopascal is equal to 10 to the power minus 3 Newton per mm square. So for example, if I will say what is the 50 kilopascal, you have to convert it. It will be going to come in objective exam. Just remember it, that 50 kilopascal just convert into Newton per meter square. The 50 kilopascal is equal to 50 into 10 to the power minus 3, because 1 kilopascal is equal to 10 to minus 3 Newton per meter square. 100 kilopascal is equal to 100 into 10 to the power minus 3 Newton per mm square. Second one is 1 megapascal. 1 megapascal is equal to 10 to the power 6 Pascal. That is equal to 10 to the power 6 Newton per mm square. Therefore 1 megapascal is equal to, just formulate what I have done. 1 megapascal is equal to 1 Newton per mm square. So similarly 1 gigapascal, 1 gigapascal is equal to 10 to the power minus 10 to the power 3 Newton per mm. This all in unit is very important. This all unit is very important. It will be going to come in the exam for exam. So this is all the concept of stress. So stress, you have, you if you understand, if you have got any problem, just kindly call me. Stress is externally load for internal resistance. It is internal resistance to the external load. Understand? This is suppose that I have here also diagram P, internal resistance, which are going to develop through external load. This is called stress. So next class we are going to start with the strength and some numerical also. This is one sample. Hope if you are going, if you are able to understand, then I will continue the video. You just give the feedback. If you are not able to understand, so I will just be try to be uh, try to what to say. If I will teach again also offline also. But anything, if you want to improvement, just give me feedback. I will try this. Thank you.